Good. Okay, so real quick, I don't need to really break this down. Anyone going to dance? No, never mind. Did you get that post? Did you get that joke? Okay. Yep. All right, so it looks like you guys pretty much rocked this. Not a ton, but a bunch of you asked me, like, is silver nitrate, like, is it losing or gaining heat? I guess that's on the later one. But whenever we give you a name of something, that something is going to be the system. It's pretty simple. All right, ice melts on a table. We got 100% on both of those. You guys are amazing human beings. All right, swimming pool, 100%. This one, when silver nitrate is placed in a beaker and dissolves in water, it takes in heat. The process is endothermic. Endo is when you enter a room, like heat enters the system. The system gains energy, good. The surroundings have to lose energy. The process, the signs are what's kicking your butt today. The process would have a positive sign. If the process is endothermic, then the process has to have a positive sign. Okay, she has one. Go ahead.
I think what she said yesterday was better. It's like I have a cold heart inside, it's inside, so it's endo, in.
This is how I remembered it, and it's up to you, but usually you don't have very good feelings about your ex. They're kind of negative feelings. So if you think your ex is a butt face, then usually you can remember that X is the negative sign. Oh, that's deep. What? Diane. Hit her up, boys. Sorry, was that? Maybe I crossed the line. That was on a. Oh my. Okay. All right. Okay. Shh. Okay. You guys did great on that quiz. I feel like let's move on. Okay, wait. One manizzle, my friends. It's Snoop Dogg for a minute. Wait just one manizzle. See? Thank you. She speaks my language. All right. Ed puzzle. I'm adding that to this list because we got as far as where the Ed puzzle needs to be. Now, this is not on there yet. I will add it probably on my prep hour. I found it yesterday. I don't know why. I didn't actually import it yet, so I got to go re-find it and make sure I like all the questions. But there will be an Ed puzzle that will go over what we do for the last 2 minutes. Okay, no more drum majors. Thank you. And what we do tomorrow. So there's an Ed puzzle homework tonight. If you do it tonight, it will make tomorrow's lecture significantly easier. Most of you are waiting to do the Ed puzzles till the end, and it's sort of pointless to do them by then because we've already gone over that. They're supposed to introduce a topic and make the discussion easier. Okay, here we go. Good. I don't actually talk about these diagrams very often because I think they confuse most people. But they're okay. So we just talk notes, and then I talk about my own diagrams or whatever. But the first law of thermodynamics is energy is neither created nor destroyed. You've known that your whole life. You've called that the law of conservation of energy. Okay. In other words, the total energy of the universe is a constant. We already said this yesterday, but if the system loses energy, it must be gained by the surroundings and vice versa. Good enough? I'm going to go fast through a lot of these today. because there's not a lot of stuff that even the most specific note writer should even be writing. There's a lot of build-up into something called enthalpy, but whatever. Entropy and enthalpy are very different. Now, they are related, but they are different. All right, so we don't do entropy for months in this class. All right. The internal energy of a system, which is E, is the sum of all kinetic and potential energies of all components of the systems, and once again we call it E. This would be a mathematical nightmare if you were ever asked to do this. So we do not really find delta or E, we find delta E. Delta E means the change in energy. And what's good about this is we just need to know the final energy state, and we subtract the initial energy state, and then we can find delta E. These final and initials would be something that would be given to us, not something we would have to make all from this math. All right, well, here it is again. So by definition, the change in internal energy, or delta E, is the final energy of the system minus the initial energy of the system. Delta E equals E final minus E initial. You okay with that so far? E means energy, or really it means internal energy, but energy is good enough. It doesn't really matter. And we did this yesterday with the heated ball, if you remember. We took the final state of the ball and said, hey, it's like 100 joules. It was 1,000 joules. So we found it was negative 900 joules that were lost. Well, technically it'd be 900 joules lost by the system. If you write negative 900 joules are lost, you're sort of wrong, but I don't mark it wrong. And neither would the AP graders. But whatever. We all right so far? Okay. If, and we said this yesterday, so that's why I'm going fast, but if delta E is greater than 0, that means that E final is greater than E initial. Therefore, the system absorbed energy from the surroundings. This energy change is called endergonic. Now, endothermic, endergonic, they mean pretty much the same thing. If it's just plain gonic, it means just energy and all forms of it. We have been saying endothermic because we've been talking about just heat. But it is fine because, spoiler alert, all these slides we're going to do for the next 20 minutes, we're going to end up doing some math that ends up canceling everything out except for just heat. So, endergonic, endothermic, they mean the same thing pretty much. All right. Now, if delta E is less than 0, then final is less than initial. Therefore, the system released energy to the surroundings. This energy change is called exergonic or exothermic. Oh, that's just annoying. Whatever. All right. So far, so good? Good. You guys rock that quiz, so pretty sure you're pretty awesome. All right. This is an equation. You don't have to use it a lot, but it is one that you do need to know. When energy is exchanged between the system and the surroundings, it is exchanged as either heat, which we use the letter Q to represent, or work, which we use the letter W to represent. So that is delta. What? I have no idea. I wish I knew, but that's just what someone chose a long time ago. It probably has something to do with Latin. Yep, most things do. All right, so that is delta E equals Q plus W. All right, then on the blue sheet it said, hey, look at this chart 100 times and make sure you understand it. If you have a black book, you went to that page and looked for the chart. You're like, where the freak is this chart? Well, it was this chart. I'm sorry.
That's totally a chart.
It's on there. It's just in a different spot. Yeah, the books are about 5 to 6 pages off generally. All right, so delta E, Q, and W, and their signs. Ooh, excuse me. This is a good qualitative question that you will see on your exam, by the way. So, if Q is positive, it means the system gains heat. If Q is negative, it means it loses heat. All right, well, that's not that bad, because how many of you have negative feelings about your ex? Or positive feelings about the person you're into? Diane definitely does have sort of that vibe once in a while. You're right. I don't either. Okay. It's not like these things are changing that much from what we kind of already feel like. But Q is heat, positive gains endo, negative loses exo. For W, this is probably the only one you really need to like memorize. W is work. Positive means work is done on the system. Okay, like we compress it with a piston or something like that. Negative means work is done by the piston up, for instance. All right, then delta E, positive net gain of energy by the system. And once again, that works well with our endo prefix. All right, and then a negative means a net loss of energy by a system. So that would be exo. I have no idea. It's on the bottom of like 169 or something like that. It's table 5.1. That's all that really matters. Table 5.1. All right. So how you would apply this on a simple problem mathematically is you would be given Q and W. So let's say yada, 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 who cares, but Q is negative 35 joules. And let's say the work done is equal to, I don't know, 50 joules. So it would ask you to find the change in energy. So the change in energy, delta E, is equal to Q plus W, correct? So you just plug it in. Delta E is equal to negative 35 plus 50. What does that equal? 15 joules. Now, you would know that the overall change would be a what in energy? Gain. It would be a gain. All right. So the energy, this would technically be endergonic. We wouldn't say thermic on this one, but that's semantics. Who really cares? We would just say, hey, the overall change to the system is a gain of 15 joules. Okay, it's not super hard. Now, I don't know. Are we okay with that? All right. There's not a lot like is exactly on the test, but it is important to understand what these signs tell you. All right. Now, what I want to know, this is the video from yesterday. It's just a picture of it now. We have this heated metal ball. I want to know the sign of Q, the sign of W, if there is one, and the sign of delta E. Will you have a short conversation with your partner about this example? Ready, set. All right, so the first thing is that one of these actually didn't happen in this example. Do you know what that was? W. There was no work done. The only way to get work done would be to like trap the gases of the steam and have it like push on the outside of a balloon or raise a piston or something like that. Don't drop your pen in disgust. There needs to be some sort of mechanical work done, because work is equal to force times distance, nothing moved. And I know the water boiled, but that's not work being done. Okay, now, so don't stress if you put something there, but now know, unless we put it in a device that we can apply like a change in pressure or something, work will not happen. So there was no work done here. So really, our delta E just depends on Q. And one more reminder, what was the system? The ball is this system, right? All right, so the system lost heat, a lot of it, right? So that means Q here is negative. All right, which means E is equal to what sign? Negative. Are we okay with that overall? If you're annoyed that the work was 0, I'm sorry. But now you know. Okay. Now, there's a lot of stuff that we've already said, so I'm going to go quick. If you want to see these, they're on the internet in multiple places. They're on Canvas, they're on BEHS Science, and you can take a picture. So when heat is absorbed by the system, from the surroundings, the process is endothermic. We've seen these same things repeating. We're just changing from energy to heat now. When heat is released by the system to the surroundings, the process is exothermic. All right. Now, a state function. This was in your notes, and it's actually not super important that you understand exactly what this example was. But a state function is something that doesn't matter on the path you took to get there. It just matters that you're there. So for instance, in 1 week, I turn 43. That's just a number, right? It doesn't matter where I've lived, what thing with my life. My age is just 43. It's independent of what I've done between 0 and 43. I'm just 43. Now, the example they give you here is that this water is 25 degrees Celsius. We don't care if it came from 100 to 25 or from 0 to 25. We just care that it is 25. Are you okay with that?
Yeah.
Thank you. Now, an example of this is from physics. A good example of a state function is displacement. Displacement is how far you are from where you began. Are we okay with that? So if I put a dot right here and right here, the displacement would be how far from here to there. That's the displacement. Oh, that's not a very straight line. But are you okay with that? Now, displacement, we don't care if I went on some random path to get to this point. It only matters where I started and where I ended. Are you okay with that so far? What? Well, that sucks to suck. Okay. Now, well, I don't care what it looks like. If displacement is a state function, then distance would not be a state function. Because the distance I travel from here, if I go from here to there, let's say it's 10. Are we okay with that? But if I go on whatever you think this thing looks like, if I go on this path, is it greater than 10? Yeah, it's like 200. So the distance I travel is a non-state function, but my displacement is a state function. You sort of okay with that so far? Yes, Diane.
So it's like you don't care about if the system lost or gained energy, but you don't care how much the change of the
Yeah, that's fine. Yep. And it really, it's just a state function, we just care what we are right now, and we don't care about anything else. All right. Now, what does that have to do with anything? Well, here we go. So, did I even read that part? I didn't. Usually we have no way of knowing the internal energy of a system. Finding that value is simply too complex of a problem. And I said this like 20 minutes ago, that we don't do that math. We just want to know where they were, where they are, and the difference. So, however, we know that the internal energy of a system is independent of the path by which the system achieved that state. In the system below, the water could have reached room temperature from either direction. Okay? That's the same thing I just said. You could go to St. George straight, Or I could go visit my dad, my sister, my friend in Las Vegas, and then go to St. George. The displacement would have been the same, but my trip distance would have been much different. Okay. Therefore, internal energy is a state function. It depends only on the present state of the system, not on the path by which the system arrived at the state. And so, delta E depends only on the final minus the initial. We do not care about what would happen between final and initial. That is meaningless to us. We just care about the current state and the state that it started. Now, however, and by the way, if you're not getting any of this last 5 minutes or the next few minutes, but it's interesting. However, Q and W are not state functions, WTH. All right? Whether the battery is shorted out or is discharged by running a fan, its delta E is the same. So what we're saying here is I can deplete a battery just simply by connecting one end to the other. And all I'm going to get out is some heat as the electrons flow from one side to the other. You okay with that? That would give me Q, but it would not give me any W. All right? But if I make the battery connect to a fan, now it is doing work. This is not a G, that's like a circle thing. All right? Now it does a lot of work and hardly any heat, which is probably false anyway, but whatever. All right? But my change in E is the same either way. The battery is dead. It was charged, and now it is dead. So the change in energy, we don't care how. We just care that it was charged, and now it is not charged. Okay? Now, therefore, when a process occurs in an open container, commonly, well, it's not a therefore, sorry. We're going to tie all this together in a few minutes. So when a process occurs in an open container, commonly the only work done is a change in the volume of a gas pushing on the surroundings, or the surroundings pushing on a gas. Now, most of us are not mechanical engineers that are going to study piston engines, so we're not going to spend any time on this. The math gods are going to shine brightly upon us here in a second. We can measure the work done by the gas if the reaction is done in a vessel that has been fitted with a piston. So if we cause this reaction to happen and it bubbles, it's going to create pressure that will make the piston go up. That's pretty cool. The system did work on the surroundings. Right? Now, if I could put something in to combine with that gas, then the surroundings, the pressure would decrease and the surroundings would do work. Now, we're never going to do this. In this class, we react stuff in beakers and micro well plates. We are not collecting stuff and seeing if it compresses or is. That will be nice. But remember this for a second. Don't write it down. But we can do this when we say work is equal to negative P delta V. Anytime you see a capital D, it really means the delta symbol. What's that? Why? I'm sorry. It is a delta. It's just how this program imported that symbol. Okay, now, here we go. This is just some math. Yeah. You guys, you never have to ask if you need to go to the bathroom. Just run. All right. If a process takes place at constant pressure, which it will in our room, we're going to do it at room pressure. All right? And the only work done is this pressure volume work. We can account for heat flow during the process by measuring the enthalpy of the system. This is the first time we're using the word enthalpy, which is what this chapter is all about ultimately. Enthalpy is the internal energy plus the product of pressure and volume. So this is the equation for enthalpy, but you will never use it. Well, I shouldn't say never. When you're in college, you do enthalpy problems with PV work, but you do not in AP chemistry. And they're not that hard, by the way, but we'll see one in a second. So enthalpy about delta, or the change in enthalpy. Now some math. When the system changes at constant pressure, the change in enthalpy is delta H, which is delta H equals delta E plus PV. Now, the parentheses, okay? That's where we get delta H equals delta E plus P delta V. Next. It can be anywhere at once. It's going to be this way because of this slide back here, right there. We want it to match that. But it mathematically, it doesn't matter. 2 times. Okay. So, match the other term. Now we're going to use the law of substitution. Substitution is awesome because then we can eliminate. Since delta E equals Q plus W, and W equals negative P delta V, so that's why we wanted it in that format, we can substitute the enthalpy expression. So here's our delta E, all right? Our PV comes here, that negative sign goes over there, that's why it's now minus W. Now, if you have Q plus W and then minus W, plus and minus means they're gone. So enthalpy works out to be just Q, which is heat. So, in pressure, the change in enthalpy is the heat gained or lost. So, what you need to write is you need to write the word, if you're a note taker, you write enthalpy, and then in parentheses, put delta H. And then here's your definition, is the heat gained or lost in a reaction. Maybe you want to write it more specific, by the system. Okay, we always define all of the heat lost or gained. We define it by what the system is doing. In a reaction, XN. Sorry. It could be an H, an N, or a U. Let me restate the whole thing. Enthalpy is the heat gained or lost by the system in a reaction. Now, if you wrote, is the heat gained or lost in a reaction by the system, that works just fine too. Well, that felt good. Oh, go again. I feel like endo and exo is pretty important in this chapter. What do you think?
Yeah.
You're wrong. It is. It's going to be important the rest of the year. The process is endothermic then when delta H is positive. Because remember, delta H is just heat now. Math was canceled out. So it follows the exact same rules. A process is exothermic when delta H is negative. Okay? So the nice thing about endo and exo, it follows the same the whole time. A positive is endo, a negative is exo, no matter what we're talking about. This is math. If you hated the math from the previous chapters, you probably won't hate this because this is not as difficult. There's less chemistry here, and it's just more math. And most of you are better at math than chemistry. All right, enthalpies of reaction, and this is what the Ed Puzzle video will be on. So please, please watch it. But we're going to say the change in enthalpy, or delta H, is the enthalpy. And this makes perfect sense, sort of, because delta, if you remember, delta has meant our final state minus our initial state. Well, the products are the final parts of the reaction. The reactants are the initial part of the reactants. And when you do a simple problem like this, it gives you, or you find them in a table, these values are all listed. And all you have to do is put them into the reaction. So I made these numbers up. But to find the delta H for the production of water from H2 and O2, and these are way wrong, so don't show your dad that's an engineer or your mom. They'll be like, he's an idiot. Those are zeros. I know that. We're making them up. All right. So you take your products, which would be 80, and then you take the sum of your reactants and you subtract them. And so you would end up with a negative 40 in this example. And since it's negative, we would say this process was exothermic. We would say if we did this process in some sort of beaker, what would happen to the temperature of the beaker? It would get warm or hot. So it makes the surroundings hotter, right? Okay, so these are simple, but they're never given to you that simple, of course, because it's science. They look more like this. No. The only time people screw this up is if you're not good at accounting. If you are an attention to detail person, you will rock this, because it's just addition and subtraction. You just have to make sure and keep track of every part. No, this is the equation we're going to use. What does sigma mean? It means sum of all. So this is the equation. Delta H is equal to the sum of our products minus the sum of our reactants. And when I say the products and reactants, I mean tomorrow.